Throughout the 17th century, the Newtonian belief that light is comprised of colored particles was still largely regarded as likely. Referring to light particles as corpuscles, Newton stated that the geometric nature of reflection and refraction could only be explained if light traveled in straight lines, and since waves do not travel in straight lines, Newton postulates that light must travel in corpuscles and not waves. This was in direct opposition to the wave theory of light put forward by Christian Huygens, who unfortunately did not have as much authority and gravitas among the scientific community as Newton did. Nonetheless, it was a sound theory, and beside its inability to eloquently explain the phenomena of reflection and refraction, it had its own merits elsewhere, such as in explaining diffraction. It wasn't until much later, in 1803, that the brilliant scientist, Egyptologist, and physician Thomas Young put forward his experiment now widely known as the double slit experiment, that effectively put a nail in the coffin of the particle theory of light, at least for another 100 years. Interestingly, the experiment, as described by Thomas Young in his first lecture, did not employ the use of a double slit at all. In the words of Young himself, the experiment had to be able to be repeated with great ease, wherever the sun shines, and without any other apparatus than is at hand to everyone. Ergo, his experiment was to be easily replicated with the most basic of equipment, which greatly strengthened its validity. It was safe to say that a sub-micrometer wide double slit was not available to everyone at the time, let alone a reliable way to generate coherent light. Instead, the experiment called for a small mirror, a pinhole, and a single piece of thick card about 1/30th of an inch thick. In Young's original experiment, using a small mirror, a ray of sunlight was reflected near a sunlit window through a pinhole on a blank wall, and within the course of this narrow ray, a piece of thick card was inserted lengthwise perpendicular to the ground, as to separate the ray into two smaller separate rays. By varying the distance between the card and its shadow, a pattern of similar parallel fringes emerged, with a central bright line always present regardless of distance. This is what we now know as an interference pattern, but also what Young wanted to achieve, as he was familiar with similar interference patterns being produced by sound waves. In contrast, if light were to behave as a particle, the light on the projection wall would exactly match the two source rays and produce just two lines of light, and nothing else. In a modified version of the experiment, a narrow laser beam is often used as a light source to ensure a very coherent monochromatic light with minimal divergence. As a side note, monochromatic light, or light with just one wavelength, is often used to clearly illustrate the interference pattern, whereas light with multiple wavelengths, such as white light, will produce multiple superimposed interference patterns, as all the different wavelengths and colors within white will interfere differently. The slits used are often narrow to improve diffraction and clarity of the interference pattern, and spaced very closely together to loosely match the wavelength of visible light. Diagrammatically, the experiment can be imagined as follows. As the coherent light approaches the two slits, they can be imagined to be moving as parallel waves approaching the screen. As the light passes through each narrow slit, diffraction causes circular wavefronts to propagate simultaneously from each slit. Areas in which two peaks of each wave intersect become areas of constructive interference and form bright bands upon striking the projection screen. Exactly halfway between the peaks of these wavefronts are the troughs of the wave, and where the troughs of one wave intersect the peaks of the other, destructive interference occurs, which shows up as dark bands on the screen instead. Mathematically, the interference pattern can be better explained if the wavefronts from each slit are imagined as sinusoidal electric field waves of light. When superimposing two waves, constructive interference occurs when the absolute maximum of one wave matches the maximum of the other, while destructive interference occurs when the maximum of one wave meets with the minimum of the other and gives a sum of zero, presuming both waves are of equal amplitude. This is to say that waves of identical frequency and wavelength constructively interfere when they are exactly in phase to give what is known as antinodal points on the screen, and destructively interfere when they are superimposed exactly half a wavelength out of phase from the other to give nodal or dark points. In the case of Young's experiment, calculating the difference between the distances traveled from each slit to any given point on the screen can be used to predict whether light or dark bands will appear on the interference pattern. When the path difference is a whole number multiplied by the wavelength, the waves will constructively interfere, while destructive interference occurs when the path difference is a multiple of 2n plus 1 over 2, where n is a whole number. A very close approximation of the angle and spacing between bright and dark bands can be calculated through Young's equation, which is derived using simple geometry, presuming that the screen is a long distance away from the slits and is magnitudes larger than the spacing between the two slits, d. The equation to find the angle theta, which is the angle of any given bright point P on the screen from the normal, is sine theta equals n lambda divided by d, where n is all positive and negative numbers including 0, lambda is the wavelength of the light in nanometers, and d is the distance between the two slits. It should again be stated that the geometry of this equation only holds true if the screen is such a distance away from the double slits that both paths from each slit can be assumed to be very close to parallel. Once the angle theta is known, the position of antinodal points or bright points can thus be calculated by the equation x equals L tan theta, where x is the position of the nth antinodal point from the central bright fringe, and L is the distance between the slits and the projection screen. As a final point, though this experiment became the cornerstone of the wave theory for many years, in the 19th century the wave-particle duality of light again became apparent with the manipulation of this very experiment, heralding the birth of the quantum age. To summarize, individual photons and particles as well are shown to interfere seemingly with themselves, even when let through these double slits one at a time, forming an interference pattern when run multiple times. However, this interference pattern only occurs when it is unknown which slit the photon passed through. If detectors are positioned at each slit to record which way the photon went with each trial, the result is that the photon ceases to interfere at all, and instead behaves eerily entirely like a particle, forming two solid bright lines at the projection screen instead of multiple fringes. Thus, ironically, in the modern age, despite such advances in the field of light and optics, the age-old riddle of wave or particle truly remains unsolved, and with quantum mechanics, perhaps the correct answer to this question will simply remain both.